Alright folks, picture this. A robot trying to make tea. Cute, right? But wait, it's opening the wrong cabinet again and again. At this point, even you're frustrated. But suddenly, the robot freezes, tilts its head, and goes, hold on, where did I mess up? Then it rewinds its mental tape, corrects the mistake, and finally gets it right. That's Agent R in action. At its core, this paper delves into how Monte Carlo tree search and self-training enable agents to detect and fix errors in real time. No waiting for feedback or post-task analysis. Just immediate learning, loop avoidance, and steady improvement. Now let's take a closer into the paper.
So LLMs are becoming the go-to solution for all sorts of complex tasks, especially in these dynamic, interactive settings. But here's the catch. The usual ways we improve these models, like having them copy expert behavior, don't always cut it in the real world. Why? Well, because when these models mess up, they often fail to recover. One mistake leads to another, and boom, you've got a cascade of errors. This paper introduces something called Agent-R to tackle this exact problem. It's a framework where the language model learns to reflect and self-correct on the fly. Instead of just telling the model if it's right or wrong, Agent-R uses this cool technique called Monte Carlo tree search, or MCTS for short. Imagine it like this. The model maps out all its possible actions, spots mistakes early on, and then dynamically stitches together corrections. It's like when your GPS finds you a new route after you've missed a turn. The key here is timing. You don't want to wait until the end of a task to fix things. That's way too late. Agent-R is all about immediate revisions. It splices those error-prone paths with corrected ones based on what the model knows at that moment. This not only saves time, but also helps the model learn more effectively from its screw-ups. Experiments in various interactive environments show that Agent-R really shines. That it outperforms other methods, improves error recovery, and even avoids those annoying endless loops. So, what we end up with are agents that are way more adaptable, acting more like real-world decision-makers. Let's look at a simple example to see this in action. Imagine a language agent trying to do something as basic as boiling water. Sounds easy, right? But without proper error correction, things can go sideways pretty fast. Look at the figure here. It breaks this down into two cases. In the first case, we've got an agent meandering through a long sequence of actions. It's opening doors, wandering around aimlessly, and generally being clueless. Eventually, it stumbles into the kitchen and finally boils the water. Success. But here's the problem. All those earlier blunders weren't addressed. The agent didn't learn from them. The rewards stay at 0 until the very end. It's like fumbling around in the dark and only finding the light switch after hours of searching. Now the second case is even worse. This poor agent gets stuck in a loop. It keeps opening the same door over and over, convinced it's on the right path. It's like trying to fix a problem by doing the same thing repeatedly and expecting a different outcome. Spoiler alert, it doesn't work. This is where Agent-R steps in. Instead of waiting until the task is over to fix things, Agent-R jumps in early. It spots errors as they happen, learns from them right then and there, and corrects its actions on the fly. By using smart techniques like MCTS, it can escape these loops and find better paths without wasting time. This dynamic approach means fewer errors, quicker corrections, and overall smarter agents. Pretty cool, right? Alright, let's break down the nuts and bolts of how Agent-R works. The tasks it handles are framed as partially observable Markov decision processes. Think of these as scenarios where the agent doesn't have the full picture of its environment. It's like trying to navigate a room blindfolded. The agent has to make decisions based on limited observations, past actions, and a set of rewards that guide its performance. It has to figure out where it is, what to do next, and if it's making any progress, all based on little clues from its surroundings. Each sequence of actions and observations the agent takes is called a trajectory. The goal is for the agent to pick the best actions at each step to maximize its final reward. To help with this, Agent-R uses something called React. This approach has the agent come up with reasons for its actions before taking them, which helps it learn and make better decisions. Now the paper also introduces MCTS, which is like the agent's GPS for finding the best paths. It builds a tree of possible actions, simulates the outcomes for each one, and helps the agent decide where to go. MCTS is great because it balances trying out new strategies with sticking to what's known to work well. This makes it perfect for solving complex, uncertain problems. Together, these tools allow Agent-R to handle long tasks, bounce back from mistakes, and adapt in real time. So how does Agent-R actually work in practice? There are two main phases. First, it uses MCTS to generate what are called revision trajectories. These are basically corrections for bad decisions the agent makes during a task. Let's say an agent is stuck in a loop, repeating the same wrong action over and over. MCTS steps in, figures out where things went off the rails, and then splices in good actions at those critical points. This way, the agent learns to recover without repeating past mistakes. The second phase is all about training the agent iteratively with these revised trajectories. Iterative. Imagine you're practicing with a coach who not only points out your mistakes, but also shows you exactly when they happened. This feedback loop is super important for self-improvement. The agent gets fine-tuned using a loss function, which basically rewards good decisions and penalizes bad ones. This process repeats, making the agent more robust over time. MCTS plays a crucial role here. It builds a decision tree of possible actions, starting with selection, where it picks which nodes to explore, followed by expansion, simulation, and backpropagation. These steps ensure the agent is always looking for smarter ways to reach its goal. By combining this with iterative training, Agent-R avoids those cascading errors and repetitive loops, creating a smarter, more adaptive agent. This section dives into how Agent-R uses different types of trajectories to make better decisions. First, we've got initial trajectories. These are the starting paths of actions and observations. From there, things can either go well or go badly. Bad trajectories take this initial path and add poor decisions that lead to low rewards. On the flip side, good trajectories start the same way, but follow actions that result in high rewards. But here's where the real magic happens. Revision trajectories. These are like hybrids, where a bad trajectory is spliced with a good one at a specific point. Think of it like switching from a wrong turn to the right path on your GPS. A signal at this point tells the agent what went wrong and how to fix it. This helps it reflect on past errors and make better decisions in the future. Rewards are super important here. For a trajectory to be considered optimal, its reward has to meet strict criteria. This ensures the agent is consistently learning from high-quality corrections. So, revisions aren't just fixing errors, they're actively improving performance. Finally, we have MCTS. This process systematically explores possible paths, balancing the need to try new things, exploration, with sticking to what works, exploitation. At each step, it builds a decision tree, evaluates potential actions, and simulates outcomes. This mix of trajectory corrections and MCTS keeps the agent both flexible and efficient in tackling complex tasks. Here, we're focusing on how agents learn from errors through two key mechanisms. First up, let's talk about transition points. In traditional methods, corrections were made at the very end of a task, which didn't give much room for real-time reflection. Engine getting feedback only after finishing a long exam. Instead, the model-guided approach stops the bad trajectory as soon as an error is detected, like pausing mid-question to offer corrections. The agent identifies this point using its current abilities and then combines the corrected part of the bad trajectory with the good one. This not only helps fix mistakes early, but also boosts learning. Next, we move to phase 2, iterative self-training. Here, the agent works with both good and revision trajectories to get better over time. One big challenge is the cold start problem. When the agent knows nothing about the environment, it relies a lot on trial and error, which slows down early learning. To fix this, good trajectories are gradually given more weight in training, nudging the agent toward the best decisions. It's like starting with easier problems and slowly increasing the difficulty as confidence grows. This balanced mix of exploration and correction ensures the agent becomes more robust, better at spotting errors, and capable of adapting to new challenges. Let's jump into the realm of experimentation and optimization. First, let's talk about the environments. There are 3 of them: Webshop, SciWorld, and TextCraft. Webshop simulates an online shopping experience where agents navigate real product data and do things like clicking buttons or searching. SciWorld tests scientific reasoning with tasks based on elementary science curricula. And TextCraft dives into crafting challenges, inspired by Minecraft recipes, where agents create items through structured decisions. Now, to make the agent generalize better across these environments, the framework combines trajectory data with broader datasets like ShareGPT. Think of this as teaching a student by mixing practice problems with real-world examples. This approach not only improves task-specific performance, but also prepares the agent for unseen challenges. The whole process is guided by a loss function. It blends data from good and revision trajectories with general datasets, ensuring the agent balances learning from corrections and exploring new strategies. Iteratively, the model collects updated revision trajectories, refining its understanding of errors and enhancing its ability to recover dynamically. By repeating this process, the agent goes from being error-prone to consistently performing efficiently, adapting its reflection and decision-making with every iteration. All right, let's get into the experimental setup for evaluating Agent-R. The experiments are happening in those 3 interactive environments we talked about: Webshop, SciWorld, and Textcraft. For each one, the system starts by sampling hundreds of tasks and uses MCTS to generate trajectories. To make sure the comparisons are fair, they account for the cold start problem by gradually increasing the weight of good trajectories during training. This helps the agent get closer to optimal performance over iterations. The training goes on for 3 iterations, and parameters are fine-tuned along the way. For instance, MCTS uses a fixed number of rollouts, a specific tree depth, and a balance between exploring new possibilities and exploiting known good actions. On the training side, the model uses the instruct version of Llama 3.18b as its backbone, which provides a strong foundation in language understanding. They're comparing Agent-R against several popular models, both open-source ones like Llama 2 Chat and closed-source ones like GPT-4 Turbo. But the evaluation doesn't stop there. They also pit Agent-R against other models trained with behavioral cloning or expert trajectories to really see what it's capable of. Finally, the metrics vary by environment. For Webshop and SciWorld, they're looking at the average reward, and for Textcraft, it's all about the success rate. This comprehensive setup gives us a really detailed picture of how well Agent-R adapts, learns, and performs in different scenarios. The results are in, and they really highlight how transformative Agent-R is for language agents. The analysis covers those 3 environments: Webshop, SciWorld, and Textcraft. They evaluated a bunch of models, from closed-source giants like GPT-4 to open-source systems like Agent-FLAN and Llama 3.18b Instruct. Here's what jumps out. First, Agent-R significantly boosts performance across all tasks. It outperforms both advanced closed-source models and agents trained only on expert trajectories. For example, it scores an impressive average of 70.71 compared to 45.46 for GPT-4. What's making this happen? It's all about revising those erroneous trajectories during training. By using dynamic self-reflection and tackling errors early on, Agent-R enables quicker recovery and more stable learning. Think of it like fixing mistakes as they happen instead of waiting until the end of a project. But not all approaches match Agent-R's versatility. While methods like contrastive learning, like ETO, show some improvement, they don't give agents that self-reflection ability. This limitation underscores why early and dynamic corrections are so crucial for sustained performance. Finally, Agent-R's impact isn't just theoretical. It delivers real improvements in error recovery and trajectory correction, as you can see in the specific case studies in the paper. This mix of performance and adaptability really sets it apart as a groundbreaking approach. The data here really digs into how Agent-R refines language agents through its approach to trajectory revision. Let's start with Figure 3. Across all 3 environments, Webshop, SciWorld, and Textcraft, Agent-R consistently delivers higher scores as training progresses. By the 3rd iteration, models using Agent-R reach scores like 48.22 in Webshop, outperforming other methods like direct revision, which capped at 42.02. This shows that the iterative refinement in Agent-R really pays off. Now check out Table 3. Here we see detailed comparisons between methods. Iterative training with trajectories from Agent-R consistently boosts performance. For example, using Agent-R-generated trajectories in SciWorld gets you a score of 48.79 compared to 35.27 with direct revision methods. Interestingly, mixing revision trajectories with optimal ones further enhances results, highlighting the value of iterative self-reflection and error recovery. Another takeaway is the downside of relying only on good trajectories. These can introduce noise, which can actually hurt performance. But Agent-R's approach includes revision trajectories that, while noisy, also contain valuable recovery info, offsetting this noise. This is key to its effectiveness, enabling agents to self-correct on the fly and improve over time. Let's dive into the data here. Look at Figure 4. It highlights how Agent-R improves action sequences. Basically, it shows how many times an agent repeats a specific action, which can be a sign of inefficiency or getting stuck in a loop. In SciWorld, Webshop, and Textcraft, Agent-R reduces these repetitions with each training iteration. For instance, by iteration 3, the repeated actions are way lower compared to vanilla or optimal models. This shows Agent R's knack for learning and refining behavior effectively. Now, Figure 5 focuses on revision lengths. This measures how far back an agent needs to go to fix its errors. Initially, models like vanilla take a long time to revise, think 11.8 steps in WebShop. But with Agent R's iterative self-training, this drops dramatically, down to just 3.1 steps by the second iteration. That's a huge efficiency boost, showing the model isn't just fixing errors but learning to avoid them earlier on. Overall, the data emphasizes how Agent-R outperforms other methods. It dynamically cuts down on redundant actions and speeds up error correction, making it a highly efficient training framework for language agents. On this page, we get a deep dive into how training with revision trajectories boosts performance and helps avoid those dreaded dead loops, finding 4 highlights that revision trajectories, compared to self-generated optimal ones, prevent agents from getting stuck in loops. These loops often come from noisy middle actions that block progress. With Agent R, agents are more likely to explore new options and get better outcomes by reducing these loops, as you can see in Figure 4. Next, Finding 5 introduces the effectiveness of multitask training with Agent-R. Instead of training models separately for each task, multitask training pools trajectories across tasks. This makes agents better at using shared knowledge. Figure 6 illustrates this perfectly, showing consistently higher scores for multitask training compared to single task. This strategy helps agents generalize their learning and do better across diverse environments. Lastly, the related work section connects these ideas to broader trends in agent learning. It highlights 3 main strategies: using prompts to summarize experiences, leveraging inference time search methods, and improving interaction efficiency through algorithms like MCTS. These strategies provide the context for how Agent-R fits into and advances this field. This page focuses on 2 crucial aspects: self-correction in large language models, and a conclusion that wraps up the paper's contributions. Self-correction is described as a vital, yet underdeveloped capability for large language models. The authors point out that current models struggle with self-correction in tasks that need multi-turn reasoning or long trajectories. Existing approaches often rely on explicit error signals, like error messages or guidance from pre-trained models, which limits how well they can be applied broadly. The paper's approach tackles this limitation by enabling language agents to self-reflect and correct errors dynamically in interactive settings, even without clear error signals. The conclusion restates the main contribution: introducing Agent-R, an innovative framework that combines self-reflection with a novel use of MCTS. This empowers agents to refine their actions and learn from errors in real time. The authors show that Agent-R significantly improves error correction and prevents those annoying looping behaviors, achieving better performance than baseline methods. By training on self-generated revision trajectories, Agent-R creates smarter, more adaptive language agents, setting the stage for future work in self-correction and interactive systems. And that's a wrap on our deep dive into Agent-R. We've seen how it tackles the challenges of training language agents, making them more adaptable and efficient through self-reflection and iterative learning. Basically, Agent-R is like a super smart GPS for these language models, helping them get back on track whenever they make a wrong turn. Who knew that a little bit of self-reflection could go such a long way, even for AI? So next time you're stuck in a loop or making the same mistakes over and over, just remember Agent-R, take a step back, and try a new path. You might just surprise yourself with what you can achieve.